Ara, en teoria, això està iniciant. A veure, Nil, mira'm si... Ara, en teoria, això està aquí. En teoria, aquí, si et fots en el telèfon i et fiques a STA...
Posi el que has tu.
Sí. No lo lee. Merda. Come on. Ahora. This? No?
What, which one is it in the folder? The first one is do and go.
Este.
So there's two. Just the one is do and go, second one is you both for this one. You both. Ah, so ambos.
Los dos.
Bueno, uno ocupa 4 y otro 90 y pico. Uno a las 2 y otro. I was saying you can open it up and just stop the second question that you can
Sí, però ara... Vale, llavors... És que clar, ara es veurà tot. Està privat encara, Però es veu? No, tindràs que fotre't amb la compte de STA al mòbil, però no la tens. Tranquil.
trobo el canal
No, però està privat. Vale, la fico en públic.
posa un públic un moment.
Vinga, va. Es veu?
Ara s'està fent.
Jo no. No, no.
Hauria de sortir sol.
Jo?
Un cop estàs al canal hauria de sortir en algun lloc i ja
I aquí li poso...
això té opcions de xat i tot, i va, comença a preguntar si que t'enviem.
Vale, bien. Per quina comença? Per aquesta, no?
Sí, aquesta és la que ja
Vale.
si no es pot fer, l'enfoquem amb ell i tal.
Ja, això.
Això se'ls passa després.
Cuidado, surt d'aquí. Si no és que es pensi ningú.
No, perquè anava una mica amb delay, no? I això que va sortir. Si això ha de sortir, doncs està bé. Perquè ha de sortir jo.
Bé.
Què passa que és el que et deia, no ho veiem aquí.
No hi ha una...
Això només ho veig jo des d'aquí. No ho pots veure si ell entra o surt de plana. Aquí estava. Per això que si tu te'n vols anar a gravar l'acceleració parcial, posar uns ordinadors.
Però tardo molt poc,
A veure.
No, no, no. Yo lo necesito, si no, ¿para? Llavors, no? Dones shape i obres aquesta... Apreteu fa un...
One, two, three.
Yes, 50%. So yeah, it's okay, it's okay.
One, two.
All right. Good evening, ladies and gentlemen. I want to share with you a little bit of experience on two things. I'm going to give you two presentations. One is about the mistake to avoid in Formula Student, and another one which is basically the case about weight and compliance. There are two things that Formula Student most of the time do not understand: compliance and inertia, intransigent simulation, and they are linked. And I will elaborate on each of them. These presentations are about 40 minutes each, so it's going to be finished before 8 o'clock, unless you have a lot of questions. Now, before I'm going through this presentation, or these two presentations, I need to say a few words about myself and how I am qualified to speak about what I'm speaking about. Well, there are two arguments. Number one, when I was your age, I designed and manufactured two things as the thesis of my engineering degree in Belgium. I design and I manufacture a race car and a wind tunnel, both. Now, I want to tell you, I was a student really middle of the pack. I had to repeat the first year. I had summer exam the second, the third year. I see a few people nodding like, well, welcome to the club, yeah. And the fourth year was good, and the fifth year I literally exploded. And the school gave me a 19 out of 20 for the thesis of my engineering degree. I literally rolled the car in front of the member of the jury, as they call it, half teachers and half of the people of the industry. I had no money, and I was about to work for Shell as a technical representative between business and engineering and so on. And I knew I was going to be bored with that job, when suddenly, out of nowhere, the second biggest Belgian company, because I'm from Belgium, called me to let me know that I was the beneficiary of an award of innovation. That money today, I calculated that 2 years ago with an inflation of 3%, that money would be 692,000 euros. I had heaven falling on my shoulder, and at 23 years old, I became a race car manufacturer. I built Formula Ford. I wanted to build a car that I was going to design, And I knew I was not going to find the money to build a Formula One. That's why I designed a Formula 4. I was young, I was dumb, and I want to tell you, every single mistake that can be done in race car engineering, I made it. So I went through, sorry for my language, I'm living in America, and you know, American is English without the F word, so I went to the same shit as you went. And you go when you design a car. And I made the same mistake. So at ease, guys, I went through exactly the same problem. The second reason why I'm qualified to speak about that, well, rest of my career, I spent 4 years designing the race car. Then I worked in the European and then World Touring Car Championship. Then in Formula 3 with a French team called Oreca. Then I went to Japan for 3 years. I worked in Formula Nippon. I came back to Europe. I worked in Formula 1. And I ended up arriving in the United States. And I did 5 years of IndyCar. That's the first 20 years of my career. In 1997, a company said, "Look, you know so much about engineering, simulation, and data acquisition. Are you interested to make a seminar about that?" I gave a seminar. The people liked it. They asked me 2, then 5, then 10. And at dinner one day, my wife looked at me and said, "You can do it a business." Well, guess what? 20 years later, we are now at seminar number 367. 13,400 people came to this seminar in 34 different countries. I thought that the demand would plateau, and it's still there. It has been diversified. We do it for the race car industry, but also the automotive industry, including now autonomous. We have another seminar coming next year. The second thing is that I'm very proud to tell you that today is Formula student number 129. I've been judging already since you guys were probably still in kindergarten. I love it. I love it, and for the simple reason that when I built my first car in 1979, I had no money. There were days I was hungry. I had no emotional support. I had no money, and I didn't consider myself as a bright guy. But I built a race car. And if I can do it, there is no reason why a group of you could not make it. A lot of people, helped me so much in many different ways. I remember the neighbor, "Claude, you need a family meal. Come have a good steak tonight. Come, go home." Okay, go. And all things like that. And now I think it's time to give back to the world. And that's why I'm a judge here, and I like to judge people, but what I like even more is after the design, it's the feedback. And I'm happy to share time. In Germany, I didn't see one car on the racetrack because I kept speaking with the student all the time, trying to give them. And the feedback is actually more comfortable for me and for you, because during the design there is a little bit of pressure. It's a little bit like an exam, you didn't do that. Tomorrow and Sunday I call that free of charge consulting. And you know, there is no stress, the point has been given, there is nothing to lose there. So that's why I'm qualified to speak, because of my racing career for 40 years, and because I went through the same shit, and because I've been judging many, many cars. You have no idea the number of design reports that is on this laptop, and the number of teams that I've seen. Now, interestingly speaking, I've done this for so many years, and the same mistake keep being present every single Formula student I go, even sometimes with very sophisticated and remarkable teams which have been winning Formula students. So I want to show this a little bit and show you, and to go straight away in the do and don't in Formula student. So some basic design error that should and can be avoided and illustrated by design pictures that I think there is a few pictures of 2017. So in the last 3 years, I took a few pictures. I took many pictures. Some of you have seen me taking pictures of car. Usually the guy look at me and say, oh yeah, you like our car, you take pictures. No, usually I take pictures of things not to do, but well, if you want to learn, come on guys, I know I've been putting pictures of cars on the internet and so on, and I try to take pictures of detail without necessarily showing which team it is. But you don't make omelets without breaking eggs. You cannot, as a community, improve unless you know what the problem is. Okay. All right. These are basic. So you're not going to show you system of differential equation. I do that in the seminar. Here, I'm going to show you a very simple thing. So I'm going to start with this one here. Rodin in bending. In your opinion, where is that thing going to break? Right there. Guaranteed. Okay. I had a very good construction machine teacher, and he said, Claude, either you looked at the real car, or you look at the drawing. He said, Claude, if something is going to break on that car, can you put the finger on where it's going to break? I said, here. Then, for God's sake, make something about it. Okay. And here, it is very clear. There is maybe some delay, yeah. It is very clear. And what's the solution? You want the linkage of a suspension passing through the center of a ball joint, of the spherical joint. You have to understand that force are supposed to travel straight. Look at this. That force is going to go in the linkage. Then it's going to make an angle to go to the Rodin on the upright. And guess what? At the moment, there is a junction between the horizontal on the picture line and the length of the wishbone. You are going to have a tension. So what's the solution? This is an example of a better car. Sorry, I think we went too quick. No, yeah, that would be the solution. Like this. This is another example. It's not as bad, but it's still bad. You have here the linkage of the pull rod, which is not going through the outboard spherical joint of the top wishbone. You see that? It's not bad, but I've seen obviously way worse than that. So you have to be very careful about that. This would have been better. You see the dotted green line there would have been much better than the red one. Okay, I've seen worse, but that's definitely better. Let me give you another example here. I'm getting synchronized. That would be a much better example. You're up, and it's not because it's carbon fiber. I need to get used to. Yeah, you are up now. Okay, it's going. Yeah, okay. So, yeah, it's like a turbo lag on this thing, it takes a little bit of time to react. Presentation sometimes. It's like a lady, sometimes you touch the wrong button. So, well, the girls are going to tell you the same thing about the guys, and they are probably right also. You see, and it's not because that suspension is carbon fiber. Yeah, it's well executed and so on. It's probably expensive, but at least the linkage, the axis of the linkage of the top wishbone there, goes through the center of the Rodin. Okay. Let me show you another example like this. Decreased compliance with good design. Look, when you have a push rod like this, the pickup point of the bottom wishbone on the upright, the outboard pickup point of the lower wishbone, the pickup point of the push rod on the wishbone, the pickup point, the Rodin, of the push rod on the rocket, the center of the rocket, the pickup point of the damper on the rocket, the pickup point of the damper on the chassis, the pickup point of the tolling, the linkage of the anti-roll bar on the rocket, and the pickup point, we don't see it here, of the anti-roll bar on the anti-roll bar link, the anti-roll bar jump link on the anti-roll bar leverage, all these points should be in the same plane. It's that simple. You know, if you have a rocker, I'm going to do it with my hand. You have a rocker like this, and you have a push rod which is not in the plane of the rocker. You agree with me that not only you're going to have a rotation, but you're going to have a bending, correct? And usually, the danger is that to cope with the bending, the guys are building a rocker which is stiffer. And as we're going to see, stiffer means necessarily in that case heavier. I keep giving always the same example. You have a headache once or twice a year. What do? You take an aspirin, and the problem is solved. When you take an aspirin, you are working on the consequence. You don't know what the causes are. But if you have a headache every day, you have to find a consequence. You have a food allergy. The air that you are breathing is polluted. You have a lot of stress. Time to change girlfriend or boyfriend. I don't know. But you are going to work on the causes of the. Yeah, I know that some of them. You know, I have to tell you, there is on the Formula SA forum, there is a guy who signed and they put a quote. And it's written, Formula SA, when you can't get rid of your girlfriend. So, or vice versa. Yeah, people are working very hard when they are dedicated. What I'm trying to say is that when you have compliance, you can work on the consequence of the compliance by making a part which is more rigid, which means thicker sheets of metal and so on. And the price you're going to pay for that is weight. Or you can work on the cause and try to put the forces on the coming from the tire, going through the chassis with some angle which have less load, the same grip on the tire, the same Fy, Fz, Mz, Fx on the tire, have less load on each picker point of the chassis and in each suspension element. So that's another one. So we are doing that, you will reduce the compliance. Okay, that is another example here. The linkage of the suspension should arrive at the node of the chassis. See that? That's very, very clear. You are going to have a bending moment there. Okay? And so it should be better if the linkage would arrive at a node of the chassis. Let me give you another example like this, which is also quite bad. You have, if you look at this, the linkage in red is not going through the node of the chassis. And I don't understand why such a mistake has been done. I need to make a comment here. And I have a gentleman here who is a teacher in aerodynamics, and he will tell you the same thing for his business. Look, my company is selling software. So I believe in simulation. As much as this gentleman believes in CFD, I believe in vehicle dynamic simulation. Yes, but there are some of the basic principles like this one, which are, I don't know why, not taught anymore in engineering classes. You have to ask. You know, a chief mechanic in racing one day said to me something, I wish somebody would have told me that 20 years earlier. He said, when you are a part, when you design a part, a wishbone, an upright, imagine that you are that part. You are a wishbone. And you have to resist force. The force is coming this way. What is the angle with which you are going to resist that force? That's simple. Okay. And I'm going to give you other practical example like that. So I wish that in green here, the linkage would have gone for the road end center. Okay. By the way, I will make this presentation in PDF also available for everybody, and you will be able to download it from Facebook. Okay, this one is simply criminal. There are people who have been executed for less than that. You cannot have the picker point of a linkage of a suspension arriving in the middle of a tube. And you know what's happening there? I'm going to tell you the number one reason that thing is happening. Because people design the chassis, then the suspension. Yeah, I see some smile here, but you know. The chassis should be one of them. The chassis is nothing else than the big bracket assembling everything. Not only your suspension picker point, but also, attaching your pedal box and your seat belts, anchorage, and all things like that. The chassis is one big bracket which is assembling everything. Should be one of the last things you should be designing. And then if you would have done that, you would have at the pickup point arriving at the node of the chassis, because you would have put the node of the chassis where the pickup point of your kinematics was. Okay? So make a kinematic design, decide your camber variation that you want in rolling, heave, and so on. But make sure that the pickup point arrive at the node of the chassis. Okay. All right. That is not bad. At least the axis of the linkage of the suspension goes through the node of the chassis, but I'm not sure that that distance was necessary. You see on the top there in red, that distance is going to make a possible flexion there. But, okay, I will not be mad when I see that. Okay, other unnecessary compliance. That's typical here. And I've seen that in this paddock very often. Look, if I take this beam and it's supported here and there, do you agree that if I push on the middle, there is a chance that I will be bending this beam? Yes or no? But if I push there, or if I push here, there will be less deflection. Yes or no? Why the hell is the push rod arriving in the middle of the wishbone? And the guys have to tell me, but Claude, we calculated in FEA, and the deflection of the bottom wishbone is only 0.3 millimeter. Well, I have news for you. And before I continue the slide, I need to tell you a story. Number one, I'm in Sebring with BMW Motorsport a few years ago. The mechanics are setting up the car, and I'm speaking with the chief engineer, and they were adjusting the rear toe. And I said to the team, to the technical director, how much do you need to change the rear toe for the driver to feel a difference? So it's not a question of more understeer or less oversteer or whatever. It's not balanced for the driver to feel the difference. Are you ready? With the fishing string, you know the distance between the fishing string, the top, the front of the rim, and the rear of the rim. 0.25 millimeter. Make the calculation. A quarter of a millimeter divided by 18 multiplied by 25.4. Why 18 by 25.4? Because it's an 18-inch rim. It is 0.03 degree. And I said, the driver can feel 0.03 degree of towing variation. And the guy looked at me and said, absolutely. The best proof is that this thing is actually, sorry for my language, the ass sensor of the driver. We measure, because there are some drivers we need to change it 0.5 millimeter for the driver to feel the difference. Wait a minute, because if the guy is sensitive to 0.03, number one, the accuracy of the measurement. I can tell you, just by locking the counter nut of the rod end of one of the tooling, you're going to change it much more than 0.03. Second one, the accuracy of the measurement. People are not using the fishing string anymore. They are using a laser sensor, a laser beam. You know, you go to any little shop or tool, you can find a laser beam for 12, 15 euro, and you attach a laser beam to the axe of the car, the axis inside the hub, so you don't care if the rim is deflected. And then you put a flag on a tube which is on the front of the chassis, and I guarantee that when you move your rear towing, the point which is like 1.7 meter ahead of the wheel, instead of your 10-inch rim, you're going to have a much bigger resolution, number one. But here's the big thing. If you have a variation of 0.03 degree and the driver can feel the difference, do you imagine what the compliance is going to do? In a car, vertically, you have three springs: the suspension, the tire, and the compliance. Do this for me. Do this at the shop. You would be amazed. Put dummy wheels, solid wheels, dummy damper. I mean, don't hesitate. A damper 25 millimeter bar, okay? Then you're going to measure the ride height, and you load the car with sandbags to simulate the downforce and the weight transfer when you are braking. No need to put 1 ton on this thing, just normal load, maybe 10% more if you want. You follow me? Measure the ride height. I guarantee that only for any Formula student, you're going to have more than 2 millimeters. So the problem is that you have one spring, free spring in series, the suspension, the tire, and so on. But the last one, the compliance, is high frequency, and it's no damping on this thing. You cannot compensate a bad kinematics with a good compliance, by bad compliance. The gods of racing are never with you. Mistake, keep adding. There is no such thing in race car engineering where a little bit of that will compensate for a little bit of this. Mistake, keep adding. So you have to be careful. And one is the compliance. So you realize, guys, that when your wishbone is going to be bending like this, guess what? The calculation on motion ratio is not the one you think it is, correct? Okay. So what do you want? You want, sorry, I need to go back to this thing. You want the push-rod axis going for the outboard point of the spherical outboard joint. Okay, I'm going to accelerate because you have a few of these mistakes that I'm going to try. Okay, this one is decent. It's not perfect, but it's close. You see the linkage of the push-rod going through the point of the outboard there. You have something similar this way. So that is decent. So reduce the compliance and you will be able to reduce the weight. Okay. All right. That is another crime. Single share. That's going to be pending. And guess what? It's on the toe ring. I guarantee that you're going to have tons of problems there. Okay. What you want is double share, a double shear, sorry, like this one. This is good. You will have, this is not a good upright in terms of the bearing, by the way. I don't like that. But this is single share. You see that? You will admire this is a Formula student about 12 years ago. You will admire the welding. Huh? Pretty good. Huh? Now, single share. Do you know what is the number one mistake that I see 95% of the time on a Formula student which has rocker? All these rocker are single share. And I guarantee the example I told you, put sandbags on the front or the rear of the car with dummy wheels and dummy shock and see how much your ride height is going down. 90% of the deflection is coming from the axles of the rocker which are bending. By the way, if they are bending, you increase the friction in the road end axis. Okay. So you really want to think about having a system which is double shared. Okay. All right. Other things that I've seen. Yeah, that one is like this one. I'm starting to be really pissed. And that is okay. That has been has been done on an Indian car. Well, there are shitty cars here also. Huh? You cannot have the pickup point, the rocker, anchorage in the middle of a tube. That tube is going to be flexing. You have a spring on a spring on a spring on a spring. And nobody's in control in that case. All right, no more comment. You cannot. The pickup point, the anchorage of a rocker should be at a node of the chassis. Okay, if you do a carbon top chassis, then of course the recuperation of the forces should be there. Spring unit, same thing. This is another ridiculous thing. You have a damper spring unit, which is on a bracket, a big bracket, and that bracket itself is in the middle of the tube. And I guarantee that the natural frequency, which is depending on the motion ratio, is going to be wrong, because the motion ratio with compliance or without, and do not forget that you have to use the motion ratio square. So when you make 10% of mistake on your motion ratio, that means you make 21% of your vertical stiffness on the chassis. So that's another thing here. That is also, sorry, I'm going too fast. This is something that you want to avoid, a pickup point in the middle of the tube for the spring damper unit. Okay. All right. The other thing is, this is a huge rocker. Are we in Formula Student or Formula Truck? Now, seriously, you would have reduced each size of that rocker by half. You would have had the same rocker ratio, correct? Guys, you need to think small. You need to think lower CG. You need to think compact. You need to center the mass from the front to the rear, from the left to the right. You need to assemble the car towards the center of gravity. Your inertia. There are three things which make a car very quick. Low CG, lower mass, low inertia. Very clear. I don't have the time to go through the calculation, but let me tell you this. When you have 9 kilo of non-suspended mass, so upright with a light wheel and so on, that's already a very light suspended mass. These 9 non-suspended mass are 15 times more important in inertia than a 4-cylinder engine. Because inertia is multiplied by the square of the radius of gyration. So you have to be careful with that. That's another one. Yeah, I went too quick for that. That's a huge rocket. It's absolutely not necessary. I'm going to accelerate. Yeah, these are rocker ratio. They have the same rocker ratio, but they are much lighter. This is obviously something which is a little bit more sexy. Huh? I mean, just, I don't know. I mean, yeah, you know, can I tell you a story here? You're going to look at me and say, why the hell does he use the word sexy in engineering? I'll tell you a funny story. I built my upright, designed my upright for my Formula 4 car 4 years ago. Oh my boy, my guys, I was so proud. My upright was so beautiful. You know, I went to see my construction machine teacher. And the guy looked at me and he said, it's not sexy. 1979. Oh, by the way, the guy was a priest. He was a Jesuit. Okay. And he said, I don't understand why you use that word. He looked at me and said, have you seen the naked butt of a girl? I don't know where to put myself. You know, I probably became red, you know, because if I say no, I haven't seen anything about the word. If I say yes, I'm a big sinner. And you look at me and say, I know you have seen one. Said, yeah, okay. Isn't that beautiful? Yeah, okay. I want your pride to be like that. I don't get it. He said, Claude, the best engineer in the world is God. And everything, look at the FIA of the finite element of a neck. You know, a neck has sustained 450 Newton vertical. Look at an FEA of a tree. It's perfect. It does exactly what it's supposed to do. And he said, everything which is pleasing to the eyes can be at the same time light and stiff. And you know it, that if you have a nice curve instead of a big angle like that, you know in FEA you're going to see more red color in that zone, correct? And you can make more stiffness with a thinner part with a large radius. You understand? So that's where the word sexy is coming. And yeah, that's it's more sexy in my opinion. Okay. Bigger is not better. Bigger is not better. Okay. All right. Yeah, and then some part of the audience was smiling and disagree with me. But, that's another one. An anti-roll bar, ladies and gentlemen, is supposed to work in twisting, not in bending. Do you see the huge distance that you have between the leverage of the anti-roll bar and the support of the anti-roll bar? Support of the anti-roll bar, which itself is extremely frail. You agree that there is a problem there, correct? Huge distance there. Your anti-roll bar would be working in bending. Okay, so totally unacceptable. The other one here, that is a classical example. Not only on the bottom, you have a huge distance as predicted between, as we saw on the previous slide, between the support of the anti-roll bar on the chassis and the edge of the anti-roll bar. But also, look at that, you have a single share on the droopling of the rocker. Going back to see the droopling of the rocker there? Single share. You remember I told the droopling of the anti-roll bar should be in the plane of the rocker. Okay. And you say, oh, it's not so much. It's not so much. Mistake will keep adding, and compliance is the enemy of the driver control and confidence. All right. A few other examples. Anti-roll bar compliance. Again, here in both cases, you have single share of the drooping. Try to avoid that. Very bad decision. Very bad design. Okay. And I saw many cars built like that. They said, oh yeah, but when we designed the car, we saw that the drooping was going to go through the push rod, so that's why we had to put a little offset there. Yeah, you know what? That's because you start to design the car when the drawings were not finished. I need to tell you a story here, 2011. I judged a team which was making their first car, University of Bologna. They won design, they finished second in the competition. There was only 17 cars in Formula Speed. That was the first year. But they won design. And I went to speak to the team captain and I said, what's your secret? He said, we have a faculty advisor with a pain in the ass. Jim, my God, if you look at me now. He will forbid us to go in the workshop unless we have every single drawing finished. Every single. And when he say every single drawing, he meant every single F drawing. The sticker of the ignition, the rivet which attached the aluminum plate for the dashboard must be in the nomenclatura all the way. You know what? They told me they built the car and the jigs in 7 weeks, and the year after that 5 weeks. And there was no surprise because they knew exactly the number of bolt, nuts, screw, rod ends, tube that they had to buy. Do not start to build anything until every single drawing is finished, especially if you are a first-year team. You know, in Ferrari Formula One, they don't wait for all the drawing to start, but these people have a little bit more money, a little bit more people, and a little bit more experience than you. Okay. All right. Another one. Big distance between the support. Another one. The pickup point of the bearing of the anti-roll bar should be at the node of the chassis. Otherwise, the stiffness of the anti-roll bar is not the one you're going to think it is. Okay, all right. I'm going to go here. Anti-roll bar is, yeah, this one is huge. And when I say huge, there are people who are making anti-roll bar, look at that, which are as big as this. I'm not kidding you. About 150 to 200 millimeter length. And they have the same Newton per millimeter, Newton meter per degree at the wheel than this huge anti-roll bar. Think small, think compact, think minimum inertia in the YY, XX, and ZZ idea. Plus another crime, the pickup point of the drooping, which is happening in the middle of the wishbone there. It's going to bend the wishbone instead of bending the anti-roll bar totally. Okay. You want another example of compliance? When I built my very first car, I ended up putting a dial gauge on the pickup point of the master cylinder on the chassis. When I was pushing on the master cylinder, on the brake pedal, the tube on which the master cylinder was attached was bending 2 millimeters. There was a part of my effort which was used to bend the tube instead of pushing the brake pad on the brake disc. Compliance. But then you have a lot of issue there of response. Okay? We're on track. That's good. Anti-roll bar design installation, of course, huge thing. Oh, look at this one, for example. It's much smaller. You can probably have more Newton meter per degree with less compliance. That means better response and better control. The same number, if not more Newton meter per degree at the wheel with that small anti-roll bar. I don't say, it's not because I showed that one better that that's what you have to do. There are even better anti-roll bars than this one. Think small, think compact, think light. That's another one. 1, 2, 3, 4, 5, 6, 7. I think I stopped counting. There are so many tubes there. And on top of that, you have 2 nodes, A and B, which are 80 millimeters apart from each other. Isn't that stupid? It is. So I'm going to tell you what's the secret if you want to make a tubular chassis. Minimum of nodes, minimum of tube, maximum triangulation, and a minimum of 3 tubes arriving at the node of the chassis. That's that simple. No, you have 2 nodes and you have so close and 6 tubes there. So the question is, try to make it minimum of a node, minimum of tube, and maximum triangulation. And actually 3 tubes arrive at the same node at the minimum. Alright, tell me about the formula truck here. You want a number? You don't have to agree with me. The number I'm going to tell you is not coming from calculation. It's coming from statistic after judging so many cars. If you have a 13-inch rim, 425 grams for an upright with no bearing, just the upright. 425 grams is decent. And for a 10-inch rim, 375 is decent. If you start to go much more than that, then you are in the big mama business. You are not in formula student design. Okay. That is, sorry, I'm too quick again. Let's see, it's a much better example. Okay, much lighter. Okay, let's go ahead. I took a tape meter on this thing. The push rod was 727 millimeters. Do you agree with me that the longer it is, the more buckling you're going to have? So you're going to have compliance again. There is absolutely no need to do it. Now, I have a complaint. There is many suspension like that I see in the paddock with a push rod, a rocker on the top of the bodywork, and then the droopling going down and the entry bar at the bottom, correct? Okay. When you make an omelette in the kitchen, it would not make sense to put the fridge with the eggs in the same floor than the bedroom, correct? You start to heat the oil, you need to rush upstairs to take the eggs, and then you come back and you crack your eggs in the fry, correct? Not very smart. Why in the hell do you take a force coming from the bottom of the wishbone of the tire, going up, then going back for the intro bar there? And guess what? On top of that, you have a tripling like this for the intro bar and a push rod like this. All these things are going to be heavy and bendy. On top of that, I see these 2 rocker springs which are facing each other, and they're outside the bodywork. But the guys are making an aerodynamic car, and you realize that the springs which are on top of the cover there are destroying the efficiency of the rear wing. Well, if you make an aerodynamic car, make an aerodynamic car, all right? I don't say that you have to do push rod. By the way, a little comment. If you do push rod, you're going to have necessarily more, you're going to have more source of compliance with a full rod than a push rod. So the advantage and the advantage, and there is no perfect solution. You're going to have to understand the word compromise. Okay. All right. The bigger the suspension, the heavier you need to think small, you need to think light, you need to stay stiff, and you need to think smart and small packaging. All right, that's another one here. Nothing to do with chassis cooling. Look at the radiator. Okay. There is a team in Germany. They have 92 horsepower. And this is the size of their radiator. You agree with me that if you have a huge radiator like that, it's going to be heavy. And the reason why they need to have a big radiator is because there is no efficiency in this. Make sense? Actually, that's interesting because I took a picture of another example here. You have the radiator there. And guess what? You have the air going in the side pod. And where do you think the air is going to go? The path of less resistance, correct? So when the hell you have a radiator? Oh, no problem, we're going to make a bigger one. And you're going to pay it for the weight. Make sense? What about having, for example, here, that's a bigger one. And I took a picture not only of the radiator, but the side pod. There is not a nice venturi guiding the air through the radiator. and exiting it. And by the way, a lot of kids are working on guiding the air to the radiator, and they don't care about extracting it. Extraction of the air of the radiator is at least as important as guiding the air out there. So of course that's going to be. Now let's give you a better example here. These people, from one year to another, they divided the weight of their radiator by 2.5 for exactly the same engine. Actually, they gained 3 or 4 horsepower from one year to another. But they divided by 2.5 the weight of their radiator because I don't remember, I think they said 2.6 kilo, and it cost them 350 grams to make this carbon fiber air conduction and air extraction with the fan at the end there. So I think light, efficient, and so on. I mean, it's pretty clear. So conclusion: weight is your enemy. Compliance too. Avoid compliance. Make it simple, make it small, and make it light. Okay. And form follow function. Form follow function. Darwin. You know, the fish want to get out of the lake, and he's going to have legs. It's going to take 2 million years, but the form is adapting to the function, correct? Yes or no? Mm-hmm. The worst thing that you can do for yourself when you design a car is to look at pictures of other cars on the internet. Define what the function you want to do, and for that you need to make a brainstorming and a whiteboard. No cell phone, no internet. Define the function, and from there you will go through the form, not the other way around. It could be that in your team you have a smart little guy who is like an Einstein guy who's going to have the light bulb solution. By looking at pictures of the car on the internet, your imagination goes from there to there. You are wiring up your brain with tons of solutions that are already existing. There is absolutely no need to copy another car. Let me give you an example. You have Indian teams who are looking at German car because, the Germans car are the best, so we need to copy the Bell car. Let me give you an example. I'm going to take 2 teams, Stuttgart and Munich. Okay? Usually they are decent teams. They are different cars. Why? Because cats are not making dogs and dogs are not making cats. The guys in Stuttgart and the guys in Munich have different culture. I don't say it's right, better, or worse. They are different. They have different teachers. They work with different companies around their own university, and therefore they build their car differently because it comes from different people. Different cats are not making dogs. Dogs are not making cats. Munich doesn't make a Stuttgart car. Stuttgart doesn't make a Munich car. So in that case, why would an Indian team with different, I don't say right or wrong, different budget, education, culture, access to software, manufacturing, and so on, would want to copy a German car? It has to come from here. It has to come from the function. So write a list of the function, then design the car, not the other way. So that's one. So I know you are hot, and me too, but we're going to save time by, instead of taking a break, I'm going to go to the second presentation, and I'm going to go a little bit more quickly. I want to explain to you the case about weight. Why and how to include minimum weight as one of the key parameters in Formula Student car concept and design. So without too many things, you have the lap time versus the power here. So you have a power curve. You use that for a single lap time simulation software. You know that we have put on the internet optimum lap, which is free of charge. It's not perfect. It's far from being perfect, but it's free of charge. And we did it because we wanted to help the student to make a first selection based on what you need to compromise between grip, downforce, drag, power, and weight. And guess what? The more power you have, the more your lap time is going down. Yeah, but between 30 and 50 horsepower, you're going to gain big, and between 90 and 110 horsepower, you're not going to gain big. But on the other hand, if you make, do you need 90 horsepower to win in Formula Student? You could, but you know what? You're going to pay the cost of that in fuel consumption. F equal ma. If you have more mass, you need more power, but you're going to pay more fuel. But if you do mass versus lap time, it's incredible. It goes down. I want to remind you also that the coefficient of friction decreases with the vertical load. So on a car of 300 kilo with driver, you could have a coefficient of friction of your tire 1 of 1.4, and the 200 kilo will have a coefficient of friction of 155. The lighter the car, the more grip, the more, not more grip, more return on investment, the more lateral force you're going to get. Okay? So weight is an issue, and you maybe want to work. So let me tell you a story. You have an airplane which is flying 4,000 kilometers. Okay? You look at me and say, are we in vehicle dynamic or flight sim? Well, you're going to see through. You say to the pilot, I want you to do 6,000 kilometers, 50% more. Okay. You know what the pilot tell you? I can only do that if you give me more fuel, a bigger fuel tank, more kerosene. Okay? Here are the bigger fuel tanks. So the problem, you need more fuel, give more fuel tank. Then the pilot look at you and said, well, the problem is that the airplane is heavier and I cannot take off. So what do you want? I need a bigger engine. Okay? Here's the bigger engine. And yeah, the guy look at you again and say, oh yeah, but bigger engine, you are sucking more fuel, so I need more fuel, you know, and because the question at a certain time you will be Now you look at me and said, what's that to do with vehicle dynamics? Okay, Newton first and second law. We are going to look at a car on a skid pad. I'm going to give you a first example. F equal ma. The car is 200 kilo, and you take 1.5 G on a skid pad. Okay? You agree with me that you have a force of 3,000 Newton, which is pushing the car towards the outside. You agree with me? 200 by 1.5, 981, that's 10, that's 3,000 Newton, correct? Yes. Now you have a car which is, 50%. You remember 50% for the distance? 6,000 kilometers instead of, okay, here 50% heavier, 300 kilo, and still 1.5 G. So you agree with me, guys, that the lap time is the same. They are both cars doing 1.5 G. Yes or no? Yes, you agree with me? All right. But you agree with me that now the sum of the force on all four tires will be here 4,500 Newton. If F equal ma, if you have the same A and you have 50% more mass, you're going to have 50% more force. Yes or no? So now let's look at the car view from the rear. And let's look only in the left-hand corner at the right rear corner. So I'm going to look at, make a zoom only on what's happening right there on the right rear. And I'm going to do that with the light car and with the heavy car. And do you agree with me that I'm going to see on the heavier car more red color if I have the same upright? Yes or no? So do you agree that with the heavier car, with the same upright, I'm going to have more risk of failure, or if there is no risk of failure, more compliance? Yes or no? Okay, a word about compliance. Between the steering wheel and the two front contact patch, I counted them, you have 24 springs. Worse than that, you have 24 dampers, and these dampers are in hysteresis. So you turn the steering wheel, and it's going to take a lot of time for the tire to start to twist and take a slip angle and generate the thing, generate lateral force. Imagine a jet fighter. The guy has the stick between the leg, and he goes like this. But because there is so much flexion everywhere, the aileron on the back, it takes a lot of time to do something like this. Do you think that the guy is going to be having a fight to fight another jet? Okay, you turn the steering wheel and it takes a long time for the slip angle to build. Do you think the driver has confidence? Doesn't, correct? So, now you can be the king of the FEA and you're going to put the rib of your upright right in the direction of the force. Good job for you. The problem is that you have 50% force, you're going to have more rib, less thickness, correct? And your frame millimeter is becoming 4 and so on. And the problem is that you're going to have now your wishbone, instead of a tube 19 by 1.5, are going to have to be 22 by 1.5, and your roll then, instead of 6, is going to be more weight. It's going to be 8 millimeter. So you have two solutions. Either you are adding more weight to go back to the same compliance, but then we are go back to the crescendo of the disaster. More weight equal more deformation, and more weight equal need more force, and so on and so on. Or you are smart and you are going to take into account you're going to make, instead of working hard, I will ask you to work smart. Let me give you a very simple example here. You are going to have here a force on a tire, viewed from the top. You agree with me that you have some force on the tire. You are only going to have the top linkage resisting the lateral force. Yes or no? Yes? Okay. Now, if you have braking, you agree that most of the force in braking will go in the rear link of the bottom wishbone leg. Yes or no? Okay. Now, if you have a wishbone which is designed like this, let's say 45 degrees, do you agree that the force that you have in the wishbone are going to be what? Zero, about 70% of the previous one? Why 70%? Because cosine of 45 degrees is 0.7, correct? So do you agree that for the same force at the chassis, you're going to have less load on the wishbone, correct? Then your rodent can be 6 instead of 8 millimeter, yes or no? Then your tube can be lighter. Then, and the chassis guy will be very interested to know that the XYZ force at the pickup on the chassis will be less, yes or no? So you don't need to have, for the same amount of Newton meter per view of your chassis, you agree that with less force at the pickup point, you can have less weight in your chassis. Think smart, okay? Now let me give you an example here. This is a question that I ask sometimes, and here the same thing. You're going to have one link in compression, another one. Look, I'm going to take this object. I'm going to throw it in the air. You agree that this object has 6 degrees of freedom, forward, backward, left, right, and then the free rotation, correct? That's the reason, because you don't want the wheel to go more quicker to the left or to the front of the car. That's why you have 6 degrees of freedom, which are locked. 2 linkage for the top wishbone, 2 linkage for the bottom wishbone, 1 tolling and 1 push-out. You are 6, correct? Okay, you want some degree of freedom control for steering and some for letting the wheel up and down. That's why you have spring entangled. Fine. So 6 multiplied by 4, because you have 4 tires, you agree that you have 24 wishbone, 24 linkage in the suspension. I'm going to ask during design final, if I see you next year, you take design final, design. You take a corner to the left. You have 1.5 G. Can you tell me which one of the 24 linkage has the highest load? And if you cannot give me an answer right there, you are dead meat with me. There are teams, when I judge them, not only they have the laptop open, and they tell me, which load case do you want? Load case, you want pure braking. 70% braking on the front, that's 35 on each wheel, 15% on each rear wheel, okay? Lateral G, or a combination, braking and lateral G, so cornering with 1.5 G and braking with 2 G, okay? You don't want to brake 4 G and cornering 4 G. It's a traction ellipse, not a traction rectangle. You cannot be a winner on both sides, okay? All right, you can make this calculation. There are teams, they are not bullshitting me, because not only the software is open, but they have binders printed with all the load case. These people have made their homework, and they know the size of the tube, the rodent that they have to have, and the force that apply at the chassis, because they have calculated the load case. Yes or no? But I want to insist, there are 2 ways to look at that. One is, this is the force when I'm braking, when accelerating, or accelerating and cornering, blah, 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 and so much downforce. This is the force on the tire, force at that moment, and that's the force in my imposed kinematics. Okay? And then you decide your tube and your chassis dimension with that. There's another way to look at that. I know the force. Now I change in the shape of my wishbone to diminish the force, as I show you here. Make sense? And that's what, and we are going back to the sexy stuff, huh? You're going to be able to do something which is both light and stiff. Okay? All right. What you need to do is something like that. You impose your XYZ pickup point in a simple software, like this, you impose the forces that you have at each force. It doesn't need to be perfect to be useful, guys. You have the TTC, you have your tire models, you have roughly, you know the FX, the FY, the FZ when you brake, accelerate, when you corner, a combination of that. And then you can recalculate the force that you have in each element of the chassis. And that's going to be, and the guy who's designed the chassis would be very happy to see that. All right, now, another one here. Yeah, that's what I'm saying here. The guy who's designed the chassis would be so happy to have the force at each of the node of the chassis. Okay, so everybody's going to be winner when you do the suspension load. Stop here. I need to tell you a story. There's a very good judge, Steve help me, in England. He was there this year. He's building race car for hill climb. I forgot his name. And he's a manufacturer of parts for Williams and for Red Bull and so on. David Gold, yeah. David Gold, G-O-U-L-D. He has a website. He judged a team and he said, show me your load case. The people everything. And he said, okay, if you are that smart, let me give you a load case here. The car goes backward because you are spinning the car. Now you jump on the brake pedal. What is the load case? He didn't have it. You know why he asked that? Because he had a customer for which he manufactured a hill climb car. The car went backward. The driver jumped on the brake pedal because he didn't want to smash the rear wing on the wall. You know what? The two lower wishbone broke. 1986, long time ago. Like an old puppy now. Indianapolis 500, March, turn 1. I saw the video. At the entry of turn 1, the rear wing is saying, ciao baby. And if you want a show, tie the seatbelt because you're going to have one. And sure enough, the car pulverized, $500,000 down. And the driver waking up in the helicopter. Thank God it was fine. They remanufactured the bracket. The bracket of the rear wing on the gearbox was what broke. You could see on the video. They remanufactured the rear wing. Make sense? 2 days later, turn 1, Indianapolis, the rear wing say ciao baby, and the second car is pulverized. Do you know why? Because the engineer will calculate the bracket of the wing versus the downforce and the drag on the wing. They never calculated when the mechanics were pushing the car forward. Which is a ridiculous force compared to the drag in the wing of the downforce, of the drag in the downforce of the wing. So I invite you to make your compliance, your load there. So that's an example. I'm going to go quickly. You cannot, it's the same thing, have the pickup point of a rocker in the middle of a tube. Okay, that is forbidden. Single share instead of double share instead of single share. Let me tell you, Formula Student Electric 2011. I'm judging, let's say, a Dutch team and a German team. The Dutch team was 82 kilowatt four-wheel drive, tubular chassis, and no wing. The German team was 82 kilowatt, big deal, four-wheel drive, no wings, and 230 kilo. Now, if you compare monocylinder, carbon tub, 10-inch, no wing, with tubular chassis, wing, 4-cylinder, 13-inch, yes, the things are not comparable. But here they are comparable, yes or no? So I went to see the German team and said, guys, can you explain to me why for the same bloody concept, you have more than 50% of the weight? And they look at me and said, but Claude, we say 35 kilo compared to last year. I look at them and said, you don't answer my question. My question is not how much did you say compared to last year, is that why, despite you say 35 kilo, are you still more than 50% for the same bloody concept? And we engaged a conversation. And at a certain time, the German team said to me, but Claude, if we put the battery of the Dutch team in our car, we don't finish the endurance. Why don't you finish the endurance? Because our car is heavier. And so the cause is now becoming the consequence. And we are back to the crescendo of the shit you have seen with the airplane. You understand what I'm saying? Let me give you an example of that car. Look at the suspension. On the German car at 230 kilo, every single road end was 208 millimeter. All of them. On the Dutch car, on the bottom wishbone, you had outboard 6 and inboard 5. On the top wishbone, you had outboard 5 and 4, and the tolling was 3 millimeter. 3 millimeter tolling. Looked like a little sewing machine stuff. Why? Because for the same lateral acceleration, if they have less force, if the same acceleration, if they have less mass, they have less force. For the same acceptable risk of failure or acceptable level of compliance, they don't need to have a big road end. They don't need to have a bigger tube. Is that making sense for you? So I'm going to tell you this. The lighter the car is, the lighter the car can be. The heavier the car is, the heavier the car can be. Let me tell you, and we're going to finish soon. Let me tell you number one things that I will do with your car. And so some of you have been seeing me judging. I will go on my knees. I will grab the tire on the inside and the rear tire on the inside, and the front of the tire on the inside, the rear tire on the outside, or vice versa. And I will create an MZ, self-aligning torque. If I can feel or I can see some toe change, you're not going to go in the final with me. Let me tell you the number one mistake that people are doing. I'm going to go a little experience. Can you come here, please? Okay, thank you. It's going to be painful, but just for a few seconds. Don't worry. No, it's really simple. Okay, here you have, look at that. You have a door. Okay, this is the hinge, and this is the door. Yes or no? And I want to enter in your office, but you know I'm really mad at you, so you don't want me to enter the office. So I'm pushing. What do you do to prevent me to enter you? Good. Look what the guys did. He pushed where? Do you agree that he pushed at the extreme? He didn't push in the middle. Do you agree that if you push in the middle to resist my force, he's going to need half of the force, correct? So guess what? The door is going to bend. He's not going to push on the hinge. Yes or no? That's pretty simple, correct? Yes or no? And did you see that he did push with a force perpendicular to the door, not with an angle? Yes or no? Thank you. Well, in that case, why in the hell do you have such a small dimension between the bottom wishbone and the pickup point of your tolling? For the same MZ, if you double that linkage, that toe base, as we call distance between the pickup point of your top or bottom wishbone and the pickup point of your tolling, if you doubled it, you agree that you have half less of the force, yes or no? And if you have less of the force, you don't need as big road end. Is that making sense? We are back to the same thing. Think function before you think compliance. And the worst thing is when I see tolling, which are tolling, guys, whether it's rear or front, should be nearly perpendicular to the inline axis of the car. Okay? Now, the light, look, I'm gonna go crazy. How stiff need the chassis torsion to be if your mass is 0 kilo? Yeah, I'm exaggerating, I'm going to walala. But do you agree with me that the lighter the car is, the less, for the same Newton meter per degree, the lighter the lighter is going to be, the less material going to be, the better it's going to be for yourself, yeah? If you concentrate in acceleration, everything, in fatigue on the tire, on the brake, and so on. The heavier the car is, the heavier it will have to be. The lighter the car is, the lighter it's going to be. Now, there is another one. Here. We have a few slides from the end. Form, follow, function. That's what you need to do there. It's not only about Formula Student. You see that Golf 1976 and that Golf 7, which was in 2030, 810 kilo, and now 1520 kilo. A lot of mass is because of safety. Cost of safety is acceptable, of course. It shouldn't be a barrier. But of course, you want the leather seat and the 7-speaker system and so on and so on. Well, what are the consequences in terms of fuel consumption? All the work which has been done by the engine engineer, the aerodynamicist, has been killed by the mass. Things are changing. The new Audi A6 in full aluminum will be 15% lighter than the previous car. An Audi A3 is 85 kilo. And you know what? It's not only about the automotive industry. If you go to the airplane, Airbus especially, I need to quickly. I have a friend of mine, ex-Formula student by the way, designing a system which looks exactly like a tolling on the front tolling. I mean, the system with 2 road ends. Okay. He has divided the weight of this thing by 8. Okay. The lighter the car is going to be, my friend, the less kerosene you will need to fly a certain distance, and especially when in the takeoff. Okay. So it's all about that. So I encourage you to think light and to think. So let me explain to you. Which upright do you prefer here? I think I know the answer, correct? By the way, I put that upright. It's real car. Didn't pass tech, but I put that upright on the scale, and it was 6.7 kilo. This is not Formula Truck, no, it's Formula Tank. So it is possible to make a car which is simple, light, stiff, aesthetic. You remember, it has to be somewhat sexy, and cheap and manufactured and easy to maintain. So voila, guys, that's basically my 2 presentations. Summary: form follow function. Define the function before you define the form. To define the form, white sheet of paper, no pictures over the car, describe what is a good team and what is a good car. There is a video explaining all this process that is on Google. If you type my name, you're going to see that. This 28-minute video. Don't care about the first 3 minutes, it's bullshit marketing about my company, but the next 25 minutes I can tell you are useful. And then, so function, then form, not the other way around. Think light, think compact, and for God's sake, avoid compliance. Please remember this. C is the enemy of C and C. Compliance is the enemy of the driver, confidence and control. And the only way you're going to be able to decide what is too much and not enough compliance is by making a transient simulation. One of these days, you're going to have to make a step test, simulation and test. By the way, a lot of team here, what they miss is correlation. Okay. In Germany last year, I had a Canadian team who showed me a 7-post rig simulation, which I was on my knees. I was absolutely amazed. And the guy took me for an intellectual and emotional roller coaster there because this thing was really impressive. Then I saw the time passing. I said, shit, I need to go back to the judging here. How did you use that software to make a good decision on your spring, your temper, and your anti-roll bar? And the guy looked at me and said, I didn't have the time. And I gave the team a 5 out of 25 for vehicle dynamics. Because if it would have been a competition on software, they probably would have a 22 or 23 out of 25. But here I'm designing a car. So you're going to have to make software, but you're going to have to have validation. So when you're going to do a step steer, you're going to make a step steer, sine wave, and so on. And you're going to make a system simulation. And you're going to have a lateral accelerometer, steering angle, a steering torque. By the way, in 20 plus years of designing, judging in Formula Student, I saw 2 cars. I don't say that they were not more. I saw 2 cars. Maybe there were more. With a steering torque sensor. If you put a steering torque sensor on the steering column, you would be amazed how much you can learn about body compliance. So anyway, you want to make a simulation, but it has to be correlated with data. So I beg you to make correlation by making tests on the track which are confirming. Okay? And you need to remember this: if the two numbers are not the same, at least one of them is wrong. I predicted 2.5G and I only have 2.3G. Maybe you tie a model, maybe the algorithm in a simulation, or maybe the lateral accelerometer is not calibrated properly, or both. If the two numbers are not the same, at least one of them is wrong. And it's not because the two numbers are the same that they are correct. No simulations are correct. All simulations are wrong. Some are useful. And I guess you will agree with me as far as CFP also.
We are not going to stay another hour.
No, definitely. And I wish maybe next year you do the same talk on aerodynamic. I'm sure you could share a lot of information with you guys. So that's it, guys. I need to say one more thing, which has nothing to do with engineering. You have, I don't know how many cars here. In Formula Student, you have about 40 electrical cars and 40 combustion. There will be one winner. Does it mean you have 39 losers? Absolutely not. Absolutely not. You're all winners here. The judge, the design judge, and the cost and business, they judge you with their brain, not with their heart. If they would be judging you with their heart, you all will be winners. I've judged teams with cars which were, sorry for my language, real piece of shit. And I met this student 5, 10, 15 years later, and these guys are doing a brilliant career, sometimes better than the well-funded Formula Student team, because sometimes you learn a lot in adversity. The goal is not to win, the goal is to learn, and the goal is to participate. It's not about the cup. If you win and you have the cup, it would be so nice to have the picture. You know what? You're going to put the pictures on a little frame, and it's going to be on your desk. And life goes on, you're going to get married, and you're going to make a little bit more money, and one day instead of the shitty apartment, you're going to buy a home, or go to a bigger apartment, and the picture you're going to put in a cardboard box, you know what? It's going to stay there. But what is in your mind and in your heart of going to Formula Student is going to stay with you. This is not about roll center, slip angle, and downforce. It is about management. It is about human strength. It's about leadership. It's about respecting yourself, because you need to sleep sometime. It's about respecting each other. It's about facing strength. It's about delivering on time and on target. That's what the goal of Formula Student is to put you in position where you're going to be one day when you attack your real career. And your real career will be different, because you're going to have a boss and you're going to have customers. And these people are going to be pissed at you if you don't deliver. Because you know, for the 2018 car, the rear wing is not ready. It's going to be in 2019. There's no consequence. But in the real life, there will be. So, what you are learning from this competition, work together, is leadership. And God knows, we need leaders in this world. So, I'm a demanding judge, but I want you to know that behind my brain, I consider you all as winners. Have fun, good luck, and I'm available if you have questions. Thank you. I think we all in a sauna here, so maybe it's up to you. If you want to have questions, we can ask in public. Otherwise, maybe we do it outside in fresh air, one-on-one, team by team, if you are interested. Good luck. Thank you, guys.